Hey, in this video, I'm going to review with you how to do well on tomorrow's quiz, valence, electron, and ion prediction. I tried to give you the slow version of the why and how you get values of the different charges, but at the end of this video, I'm going to give you the quicker version. Okay, so we started off this section talking about how to draw Bohr models. And Bohr models are not the way electrons are actually organized. They're organized into regions called orbitals. But the Bohr model allows us to understand how to predict the number of valence electrons each atom has. So if we have sodium, and we have sulfur, and we have carbon. Okay? So sodium has a total of 11 electrons. Carbon has a total of 6 electrons. And sulfur has a total of 16 electrons. So I'm going to write that here. This has 6, this has 16, and this has 11. So when we did this in class a couple days ago, we said that the first energy level can only hold 2, the second energy level can only add 8, and the third energy level can only have 8 as well. Again, this is not exactly correct for thinking about the way atoms are actually organized in orbitals, but again, I'm going to skip that idea for now in the quantum mechanical model. You can worry about that when you watch the Avengers this weekend. So it's 2, and then it's 4, 6, 8, and 10. And you notice there's 1 left, so that's the 1 valence electron. So sodium has 1 valence electron. Sulfur has 16 total, so again I'm going to draw it in pairs because that's the traditional way it's done. Again, the reason for that is not important right now. But I'm going to ignore that Java update as well. Okay, so that's 10, and I'm going to add 6 more. 2, 4, and 6. So you can see that sulfur has 6 valence electrons. And then carbon has 6 electrons total. So there's 2 in the first energy level, and then 1, 2, 3, 4. So this one has 4 valence electrons. So we learned in class on Wednesday that the pattern of valence electrons are these A numbers. 1, 2, 3, 4, 5, 6, 7, 8. So the A group number is equal to the number of valence electrons in an atom. Again, we're going to ignore the transition metals and the inner transition metals because those follow other kinds of rules and patterns, and it's not important right now. So we're going to focus on only the representative elements, these ones that start with A next to the group number. The exception to this is helium. Helium only has 2 valence electrons, and that's because if we're counting the electrons on the outside, helium only has 2 to begin with. So it has 2 valence electrons on the outside. So you should know that one. The pattern is 1, 2, 3, 4, 5, 6, 7, 8, with the exception of helium, which is only 2. What we talked about today is that we looked at these ionization energy graphs, and we saw that some electrons are easier to remove because they require less energy. Remember, it's the energy required to remove the most loosely bound electron. And to think about why it's the most loosely bound, it's because it's the furthest away. It has the lowest attraction. So it's going to take the least amount of energy to remove. See that sulfur has 6 electrons that are easy to remove. You notice that they group up, right? And you notice that there's about 10 here. I'll put a rectangle around them, that are more difficult to remove. They take more energy to remove. Same thing here. There are 10 electrons that are these core electrons that are more difficult to remove. You can remove them, but you got to put in a lot more energy. Notice the scale is logarithmic, meaning it's multiplied by 10 on every line. 500, 5,000, 50,000, 500,000 kilojoules per mole. But notice the scales in each graph are actually different. So sodium's electron is actually a lot easier to remove than sulfur's. So we also looked at an electron affinity. This is the adding of electrons. And you notice that actually most of the values here are negative. That means energy is being released instead of being put in. What that means is that adding electrons is actually advantageous to an atom. Atoms like to have more electrons, but there's some atoms that really want electrons more, and that's F, Cl, Br, I, and At. And if you notice where they are on the periodic table, they're actually over here. They're one step away from the noble gases. And as you learned, right, the noble gases, those are the ones that are the most stable. They don't undergo many reactions at all. In fact, helium and neon don't make any compounds. The other ones do, but very few. So they're the most stable. Every other atom is trying to be like them on the periodic table. So fluorine, chlorine, iodine, these ones right here, these are called the halogens. These only need one more electron to become like the noble gases. So what we're learning here is that some atoms like to gain electrons because it's advantageous for them, and some atoms like to lose electrons because the advantage is for them to lose them to become like noble gases. So when do they gain, when do they lose? It depends on how close they are to being like a noble gas. So let's do some examples. Well, krypton, as you can see, is a noble gas. So it's already stable. It has 8 valence electrons. It doesn't gain or lose electrons. So what is its predicted charge? 0. Or you could write neutral. Or you could write no charge. Oxygen is right here. It's in group 6A. So it has 6 valence electrons. So really there's 2 choices here. Oxygen can gain 2 to become like neon, to gain 2 electrons, or it could lose 6 to get all the way back to helium, right? 8 minus 6 is 2. So it could lose 6 electrons. So you gotta ask yourself, is losing 6 electrons more likely to happen? Or is gaining 2 more likely to happen? And I hope you can understand that thermodynamically, right, when there's no brain involved, that this is more likely to occur. So oxygen gains 2 electrons, and it's going to become negative 2. Now, why is it gaining 2 to become negative 2? Because electrons have a negative charge. Electrons are negative. So if you gain 2 things that are negative, the atom becomes negative. If it loses things that are negative, it becomes positive, which is the next example. Calcium is right there. It has 2 valence electrons. It was going to lose 2, because the other choice is for calcium to gain electrons until it becomes like krypton, right? Very unlikely to follow that long path. It's more likely to lose 2. If it loses 2 electrons, it's going to become plus 2, right? You lose 2 negative charges, you become plus 2. And then lastly, there's carbon. Carbon is one of these weird atoms where it can't decide whether it wants to gain 4 electrons or it wants to lose 4 to become like helium. So it doesn't play this game of becoming an ion. An ion is a charged atom. It doesn't become a charged atom. So it has 4 valence electrons, but it neither loses nor gains electrons. It doesn't become a charged atom at all. You can't write 0. You gotta write Na. Doesn't apply. Not applicable to this question. Because all of the atoms in that group, right? All the atoms in the carbon group, right? The general pattern, especially for carbon and silicon, is that they don't become ionic compounds. They do this other kind of bonding called covalent bonding. Ionic compounds are about forming ions, charged atoms. So what's the general pattern? The general pattern is that group 1 atoms form +1 charges, group 2 form +2, Group 3 form +3. And then we start at the other side. Noble gases don't become any charge. Fluorine and halogens become -1. Oxygen in their group become -2. And nitrogen in their group become -3. And again, you'd write Na for atoms in the carbon group, that 4A group, because they don't like to lose or gain electrons. So I hope that's a helpful review. And if you have any questions, please message me. The quiz looks very much like this. So I hope this is a good review for you. Thanks and have a good night.